presenters today. Our first is Patrick Anderson. He is our product application specialist, and he takes our RaySafe products and puts them into everyday situations. He's here to help with how to perform tests, data outputs, and specialized applications. Patrick draws on his education in the nuclear physics and will do the majority of our presenting today. Thank you for sharing your camera. Also joining us today, we have Matthias Gustafsson. Matthias, if you wouldn't mind sharing your camera as well, giving us a quick wave. Hello there. Matthias is joining us from our R&D engineering department. He's our technical product lead for the RaySafe X2 system and was actually integral in the fundamental design of the CT sensor that we're going to go through today. He uses his PhD in atomic physics, and he's here to help us answer the toughest questions we've got in the Q&A. You'll hear from Matthias a couple of times throughout the presentation today, but the majority will also come from Patrick that we saw a little bit earlier. Okay, on that note, gentlemen, would you like to take it away?
Thank you, Lindsay, and hello, everyone. Good to have you with us today, and thank you for taking the time to participate in our webinar. So this is the content of today. We will start with an introduction to the CT machine and how they operate. Then we will talk about some measurement principles and how one can use the RaySafe X2 CT sensor to visualize how the machine is operating. And finally, we will talk how to make CTDI measurements and CTDI calculations using Phantom. But let's start talking about the CT machine and how it differs from conventional radiography. In conventional radiography, it gives you a fairly short exposure and gives a high resolution 2D pictures. A CT machine uses a thin beam that rotates around the body. And there are mainly two different ways the CT machine can rotate around the patient. The first way is that it makes a full rotation around the body. Thereafter, the patient is moved and another rotation is made. All these signals are then processed by a computer and it creates image slices of the patient. And these slices makes it possible for medical staff to investigate different layers of the patient's internal. A more modern approach is not to make a full rotation before the patient is moved. In the helical or spiral approach, the patient is moved continuously through the machines as it rotates. The patient moves the same distance, but at a shorter time. And more sophisticated computer algorithms makes it possible for the machine to create slices of the body. And a continuous movement makes the experience a lot more pleasant for the patient compared to conventional CT. Since the total time for the investigation is lower, it reduces the risk of movement by the patient, and movement will decrease image quality. If we look inside the CT machine, it contains of a rotating tube and a receiver. It does not always have to start from the top. It could also start from an angle as well, depending on the settings. There is an ISO center, which is considered as the center of the machine. And this center is used as reference when it comes to measurements and calculations and so on. There is also a field of view, and the field of view is defined as the dimensions of the exact anatomic region included in the scan. And finally, there is a couch where the patient is lying. If we look at the tube from the side, we can see the beam width, which varies from machine to machine and which setting the machines are using. And the beam width is also defined at the ISO center. A CT machine can capture signals from many parallel channels simultaneously, and each channel is referred to as a slice. And the slice thickness is also defined at ISO center. even though the slice thickness becomes wider and as we move away from the isocenter. The beam width is the slice thickness times the number of slices. And this is just an example for how it may look, the size of the numbers and so on. Okay, that was a pretty high level explanation of how a CT machine is working. And now we will proceed to talk a little about our RaySafe X2 CT sensor. It's a nifty little sensor designed to help you measure on a CT machine. Our CT sensor is an ion chamber designed for CT measurements. It means that it picks up radiation for the full 360 degrees rotation of the CT X-ray tube. And as our other X2 sensors, the sensor is connected to the base unit, which control and stores data. The sensor itself is an ion chamber with an electrometer built into a compact unit. It has a diameter of 12 millimeters that fits into all standard holes of CTDI phantoms. The active length is 100 millimeters. Both ends and the center of it is marked with white circles to help with the laser alignment. And between the lines is the active volume. Just at the edge of the active volume is a temperature sensor. And in the electrometer, there's also a sensor for barometric pressure. This gives us a signal that is automatically temperature corrected for the air temperature inside the ion chamber, not inside the room if the temperature should differ. It is pressure corrected, and then the data is transferred as a digital signal to avoid cable interfering with the accuracy of the measurement. The CT sensor provides up to 4 parameters and a waveform. It will give you dose rate with a waveform, time, and the dose length product, the DLP. And the ion chamber, the CT sensor, shares property with other ion chambers. This means that the whole volume must be irradiated for correct readings for dose and dose rates. If only a part of the ion chamber is irradiated, one needs to apply corrections and recalculate the readings. For correct DLP readings, the radiation must be within the active length of the ion chamber. But what do we actually mean by dose length product and DLP? Well, the measured DLP value is the dose in gray times the length in centimeters. The length is 10 centimeters of the ion chamber. In a CT machine, the dose is related to length and volume. So the DLP is the main parameter for CT dose measurements. And exactly how we will use the DLP parameter we'll come back to later on. If you would like to read our manual and how to use the CT sensor or any other instructions, they are easily accessible in the base unit. You just press the help button and all our manuals and instructions can be read directly from the base unit. Okay, we have now covered how our CT sensor is designed. We will now continue with how to use the sensor, and we will start talking about measurements free in air. And measurements free in air means that we place the sensor free in air without any phantom present. And some measurements are better made free in air. A CTDI Phantom, it's a rather heavy item, and it's hard to carry. It's hard to carry with you, and therefore one should try to make as much measurements as possible without using the Phantom. And X-ray general output, time measurements, creation of calculation factor, and constancy test is just some example of tests that preferably are made free in air. But one must check if the local regulation finds it acceptable to do these types of measurements without a Phantom. So it can differ from country to country. Just to give an example of how a constancy test may look. So the goal is to check the X-ray tube output variation over time. And commonly analyzed parameters and machine settings for constancy testing is the KV, it's the mass or MA and time, the beam width, and the field of view. And you try to see how this parameter varies over time. And once again, remember to place the sensor correctly in the isocenter, so you are certain that you place the sensor at exactly the same position every time you do this type of measurements. When you're performing measurements free in air, one must look at the waveform to evaluate if the sensor has been placed correctly in the isocenter or not. This waveform that is showing is flat, meaning it has seen the same dose rate throughout the whole rotation. Since the output of the tube should be constant, one can then make the conclusion that the sensor has been placed correctly in the isocenter, where the distance to the tube is constant. And we will now try to give you a little question to see if you can interpret a waveform. The sensor, it has been misplaced somewhere in relation to the isocenter. The tubes makes one rotation according to the direction you have received. According to the direction, and you have received the following waveform. So, where do you believe the sensor has been placed? Is it below, above, to the right, or to the left of the isocenter? And we will leave it.
Yeah, let me jump in here. We're going to leave this up on the screen for just a little bit so you guys can see the images, and then I'm going to launch the poll and you guys can enter your answer in there. But inside of the poll, you won't see that image, so I'm just going to give you a few more seconds of looking at that, making sure you've got all the information before I hit launch here. Okay, here we go. I'll leave this poll open for about 30 seconds or so. Once we get a good percentage of people answering, you should see up on your screen a quick poll and the answers that were the options before. Give it just a little bit more time. We're at about 75% of the people have voted so far. Okay, I'm going to hit close on this poll and let's see what everyone came up with. So we have 15% of the people said the first answer, below the ISO center. 26% said above the ISO center. 15% said to the right of the ISO center, and 44% said to the left of the ISO center. So we've got a mixed amount of results here. Patrick or Matthias, let's talk about this one.
Yeah, interesting. So the correct answer here is actually D, to the left of the isocenter. And I wonder if you, Matthias, if you are able to elaborate this a little bit more to explain why D is the correct answer.
Yes, I can do that. So could you please put up the next slide? Exactly. So here in this picture, it's really all about distance to the X-ray tube. And in this case, we see that there is a maximum. The dose rate is at its highest towards the end of the scan. And this means that that's where the sensor is the closest to the tube. So in this case, we have the tube starting up at 12 o'clock position, and then it moves around to 3, 6, and then somewhere close to 9 o'clock is where you have the biggest dose rate again, and that's then where, in this case, that you probably misplaced the sensor a little bit. So this is one of the things I often use this dose rate waveform both to check positioning, but also sometimes if I'm sloppy with my notes and if I go back and look at exposures I have done earlier and I'm not sure, for example, as we will see later, if I did a measurement in a phantom or not, you can use this dose rate waveform to check your assumptions that exposure number 5 was really what it was in your notes, or if you forgot to write your notes. So you can use this dose rate waveform to get some additional information about positioning, or also, as we'll see later, if you were in a phantom or not.
Perfect. Thank you, Matthias. I hope you all find this enlightening.
And also, Patrick, maybe you can say how you get to the waveform if you use the X2, how you get to see this.
Oh, the waveform, yes. When you have done your measurements and you received your parameters on the base unit, you can just click on the dose rate field on the base unit and you will receive an enlarged picture of this waveform. Another way, which we will go through in a few minutes, is to use our RaySafe View software, where you can have even larger and more detailed curve forms or waveforms. But we will come back to that in a few minutes. We will now leave the measurements free in air and continues with one of the main topics for the day, the CTDI measurement, using the RaySafe X2 CT sensor. On the picture, one can see an example of a CTDI phantom used for measurements and CTDI calculations. And the purpose of this phantom is to simulate a patient, and the calculations are made to estimate the total dose to the patient. And you have different sizes depending if you would like to simulate the chest of the patient or the head, for example. CTDI reported by the CT machine for actual scan is defined CTDI-W, or weighted CTDI. It is most often measured with a 100mm iron chamber. The weighted CTDI is calculated based on measured results where the sensor is irradiated at several points throughout the CTDI phantom, combined with different settings on the machine. As one can see from the picture, one should do measurements in the center hole and in the 4 outermost peripheral holes. And the measured values can then be inserted into an Excel template to calculate CTDI-W. But first, let's take a look on how it may look when doing a CTDI measurement. So we have a phantom placed on the couch in the ISO center. We have the X2 CT sensor placed in the center hole, and we are ready to measure. So let's do a full rotation in steps. As the rotation becomes more and more complete, the waveform starts to take shape. When the beam passes through the couch, it will absorb some of the radiation and the measured dose rate will then decrease. So now we have a complete rotation. And when looking at the waveform, one can, from the couch part of the waveform, see where the rotation starts and stops. And this is how a waveform may look from the first peripheral hole, a second, a third, and the last one. And by using the DLP values from these measurements, we can quite easily calculate CTDI W with the same formula I presented earlier. But doing all required calculations for CTDI is rather time-consuming, and human errors can easily be made. And a helpful tool to acquire the CTDI parameters for the user is to use our Excel templates, for example, together with our software, RaySafe View. The RaySafe X2 system saves and stores all measured data inside the base unit. All the data can be retrieved at any given point, but it can also be transferred to our RaySafe software, RaySafe View. And here it can be used for deeper analysis, saving of original measurements data with all the details, and you can also use it for live export to Microsoft Excel and our templates. The RaySafe View software, it is free of charge and is included when you buy our systems. It can also be downloaded from our RaySafe website. Our Excel templates, they are also available to download from our website, or you can directly download them from the RaySafe View application. By hitting the File button. The templates are meant to serve as an example, and it will give you inspiration and help you build your own templates. They are all unlocked with all the calculation for you to see and to copy and to do whatever you like. The manual of the RaySafe View can also be found on the web page, but it can also be found in the software if we just click on Help, and it will open our RaySafe View manual. If we look at the Excel templates that are included, they also have detailed instructions on how to use them and how to arrange your measurement setups. All this to help you make as accurate measurements as possible. But let's have a closer look at the CTDI template that we are sharing. So we will simulate a CTDI measurement with 4 different kV settings using our body phantom. First, we have a bright red field. We need to tell the template the beam width. So let's do with 20 millimeters. It is also a good idea to have the set kV and the mass values filled in as well. And we are now ready for our first measurement, which is in the center hole with 80 kV and 300 mass. After we finished with the center hole, we make one exposure in each of the peripheral holes. Then the template calculates the average DLP and finally also the CTDI or the weighted CTDI. Then you redo the measurements for the other KV and the mass settings. The procedure for the head phantom is exactly the same. Just one clarification with this template as well is that you do not have to manually insert the measured value. If you have the correct setup with the base unit and RaySafe View, your measured values will automatically be exported to the template, and it will give you all these CTDI parameters. Okay, this slide actually concludes my presentation about CTDI, and I hope you have found it informative. And I would really encourage you all to use our pre-designed Excel templates, not only for the CTDI, but for other modalities that are also included in the template package if you download it. And we will now start our Q&A. And Matthias will help me to try answering all your questions as good as possible.
All right, if you gentlemen would also share your video cameras at this point, just so we can see you. All right, thanks guys. We have a couple of questions in our Q&A that have come in throughout the presentation today. If you are have any questions for our experts here today, go ahead and put them in the questions and answer box that you'll see on your GoToWebinar toolbar. So let's get started. Is it possible to read out temperature and pressure without irradiating the sensor?
Yeah, I'll take this one, and that's a very good question. And before answering, I only want to stress, since it's sometimes a misunderstanding, that when you measure those with X2 CT sensors, you don't need to apply temperature and pressure correction. They are automatically, that's automatically being done. And I sometimes see those being applied by people because you learn that in class and you see that in textbooks. But with X2, you should not apply a manual correction because it's done automatically. If you do want to know what the temperature and pressure was, there is a way to do that. It's a little bit hidden because we didn't want it to be too obvious, just so that people not by mistake apply a manual correction. But it's if you use RaySafe View to view the measurement on a PC, and then you export to Excel, you can see in the Excel export what the temperature and the pressure was. However, that does require you to irradiate the sensor. And in this case, the question was, can I do it without irradiating the sensor? And unfortunately, the answer to that specific question is no. You can only do that if you have made a measurement, if you have made an exposure. And then you need to do, again, view the measurement on a PC and export to Excel. I think you can also, I'm a little bit unsure, I think you will also actually be able to see the pressure and temperature in RaySafe View itself, but I am a little bit hazy on those details. You can for sure see it if you export to Excel.
Okay, thank you for that. We have another one in here. Can the CT sensor be used as a transparent sensor?
Yeah, it can be used if there, for example, is automatic exposure control. But since it is an ion chamber, it will pick up backscatter. So if you're interested in backscatter photons, We also have an application note on our web page on how to calculate skin dose, for example, while using the CT sensor. Or do you would like to add something, Matthias?
Yes, I actually have some props here, so I think I'll make use of them. So here you have what many of you probably are familiar with is the X2 RF sensor. And the X2 RF sensor only measures radiation that comes from above. It's shielded from below. You can see that I actually have one with the cover off. So I think you can see here. You see there's a little box, shield box here. You see that it's only open here at the top, and anything that comes from below is shielded. That radiation will not be picked up by the RF sensor, while the X2 CT sensor, being an ion chamber, will see radiation both coming from above or from where your X-ray tube is, and also any kind of backscatter from below or side scatter. And it's also then not really visible on an image, and therefore does not affect AEC.
All right, even with props, I like that. Thank you, gentlemen. What are the steps of measuring dose if the beam width overlaps the active volume of the chamber?
Excellent. Another question where I can use my prop. Great. So again, here is that's a very good question, by the way, because on modern CT machines you can have beam width that are 160 millimeter is not that uncommon on new fancy scanners, but here the active area or the active length is only 10 centimeters. And what you do then is that you align, let's say that the laser cross is here where my finger is. So you align the edge of the active length with a laser cross so that you measure half the beam, and then you make an exposure. And then you move the chamber like this so that you capture the other half of the beam, and then you make another exposure, and then you add those two together. That's if you want to measure free in air. So basically you chain two measurements together. First one half, and then you move and measure the second half of the beam. If you want to measure CTDI and not measure free in air, then there is a protocol for that. So the standard that specifies CTDI 6601-2-44 has an amendment that specifies how to measure CTDI. I'm not going to go into full details here because that would be a very long answer, but the basics of it is that you measure CTDI first for a 20 millimeter beam. So you measure CTDI in your phantom, as you usually do for a narrow beam. And then after that, you measure free in air with 20 millimeter. And then you measure again at the beam width you're interested in, let's say 160 millimeter. And then you measure free in air using the procedure I described, that you chain two exposures together. And then you can use that to scale your 20 millimeter CTDI to your larger beam.
Okay, thank you for that one.
Yeah, and that's also covered, by the way, in the Excel template. So the Excel template can handle that and has instructions for how to do it in more detail.
Okay, thank you. When do we need to do CTDI measurements? Is it annually or after certain incidences with the tube? There's also one that is similar to this as well. It's, do I need to do the tests when the machine goes down and is back online?
Okay, I can take this one as well. Yes. So first is that this answer is going to be different depending on where you are. That's of course down to your local regulations. So I will not be able to give an answer that covers the whole world. But what I can do is say what's most common, and the most common, two common standards to use. One is the IEC standard for this, which is we're going to have to look at my cheat sheet here. So it's 61223-3-5, which specifies, and I have to look at my cheat sheet again, so I don't know these things by heart. So it specifies that when you do acceptance testing, and also after you have changed tube or any other major change on the scanner, then you should measure CTDI in a phantom. You should measure what's called CTDI vol, and then you should compare this with what the scanner reports, and it shall not deviate by more than plus minus 20% or plus minus 1 milligray. So that's what you do during acceptance testing, or when you have changed tube or other major change on the scanner. And then for and otherwise you should do yearly testing. And when it comes to those, then you have the choice now to do constancy testing, where you don't need to pull out your phantom, but you can measure CTDI free in air without a phantom, and compare with the values you recorded during acceptance testing. So you can only do a constancy testing without using the phantom. The new standard, at least the newest revision of the standard, allows that. You can also, if you'd want, use your phantom and do a CTDI measurement as well, but that's constancy testing and that's yearly. That's the IEC standard that I know is very common to use in Europe, and I think some parts of Asia as well. But again, you'll have to know what your local regulations state. And then you have the ACR, Quality Control Manual, ACR, American College of Radiology, which is used in the US, and I think also in some parts of Asia, but I don't know the specifics there. So again, you need to know your local regulations. But the ACR manual, it states that you should measure CTDI in a phantom annually. So you should test 4 protocols annually: adult brain, pediatric abdomen, and adult abdomen. So there it's annual as well, but in that case, they require you to do CTDI measurement every year, while the IEC standard allows for constancy testing measuring only free in air.
Okay. Got a couple more questions, and if you have any, please put them in the question box in your GoToWebinar toolbar. Is it possible to measure the beam width using X2?
Well, we recommend the user to use a thing called a chronic film, which I also have some things here at my desk here, so I think I have here. So this is a type of paper, one can say, that would change color when it's irradiated. So if you place this paper in the field and you make an exposure, you will see the beam width on the paper, and then you can easily measure it by measuring the size on the beam on the paper. So that's how we recommend the user to measure beam width together with our X2 system.
Okay. How can the X2 measure KV on a CT machine?
Should I take it, Matthias, or would you like?
You go, Patrick.
I also have an RF sensor here. We cannot measure kV with the ion chamber, since it only will give you dose rates, DLP, and time. But you need to use our RF sensor, which you place in the beam instead. Just make sure that you fix the tube at 12 o'clock before you make an exposure, so you will get the beam straight on the sensor. Otherwise, the kV readings might be a little bit sketchy. But you need to use our RF sensor to get the kV on a CT machine.
Yes, and also if you want to measure kV, then you need to make sure that the tube doesn't rotate, because again, the RF sensor is only sensitive to radiation coming from above. So you need to make sure that you have locked the tube in the 12 o'clock position, which you can usually do by taking a scout image. Or if you're able to go into service mode, which I guess most of you aren't, but if you are, then you can also do it that way.
All right, well, thank you, gentlemen. That is the end of our questions and answers section here. So I really appreciate you fielding these technical and complicated questions. So we still have our experts on the line for a couple more minutes. I'm going to go through a few more housekeeping items before we take off today. So if you do have any more questions, feel free to put them in the questions box in your toolbar. So we did, again, want to say thank you for joining us today. If you do want to learn more, we've got our Empower webinar series available on demand. If you go to flukebiomedical.com and then you go to the Knowledge Center in the drop-down, there is a webinar section in there, and that's where you get our on-demand webinars available to watch. Also in the Knowledge Center drop-down, there is the Fluke Biomedical Advantage Training Center. And so if you just click on the training, then we have a on-demand, free, self-paced training for more helpful tutorials and a lot of other subjects. It's really robust and a lot of education to be learned from there. One more quick question before we take off today. Is there an X-ray beam emission standard value range given the filtration?
So I take this question as asking, are there standard values for those reference values? And my answer to that is the ACR quality control manual gives reference values for certain types of protocols. So, for example, an adult brain is 75 milligray. An adult abdomen is 45 milligray for the CTDI vol value. So those are basically value that is around what you would expect for a good control, good protocol. Let me see here if that's what was meant. Otherwise, if the question is more, is there are there standard beam qualities? Then I would say that there are lab-defined beam qualities called RQT. I don't think that's what was asked either. I think I understand. Is there, if I have a certain filtration, what dose could I expect? I think that's what's meant. And in this case, yes, there is. However, I can't answer that question on the fly. It's quite easy to calculate there is a program called SpecCalc that I use that is free for academic use that you can find when you Google, where you could enter your filtration and your KV, and then you can see and the distance you have from the X-ray tube. And in that case, you can calculate how many microgray per MAS you could expect. However, it's not giving you exact numbers. It's not something I can do on the fly. But this SpecCalc program is something that I have used quite a lot, and it's free for academic use. So there you could do that yourself.
And gentlemen, let's give a quick wave and thank you again for joining us this for our session today on CTDI measurements.